Welcome to this demo that is going to show you some simple principles of Intromit. The video is a capture of a session inside Emacs editor. In the upper buffer, we'll write some code. The lower one is for the shell session to demonstrate the functionality of Intromit. Let's take a look at our environment. We are running in a new Linux box with a standard compiler and Python interpreter. We need it because Python backend is going to be sought. Note that Intromit is still in alpha version. Now let's write a minimal piece of code to get a global vision of the process. The demo class has only an integer member and a simple constructor that initializes it. To simplify the process, we'll also write a simple makefile. The first rule is used to generate Intromit metadata product from compiled library. The second rule makes a dynamic library with debugging information from test source. All compilation will be done inside Emacs. Exit status of make command is shown in Emacs minibuffer. So at this point, from the source code, a dynamic library has been generated, and from this ELF file, an Intromit metadata product. This metadata describes the structures, functions, global variables, inheritance relations, and the rest of information that describes the program, including specific source commands. Intromit backends take advantage of this metadata to get higher functionality. This allows, for example, using our C or C++ code into higher level languages. This is precisely what is going to be demonstrated here with the embedded Python backend. Let's take a look at this backend. Intromit test directory holds a sample program showing it. Let's run it. At a first glance, this is like an ordinary Python interpreter, but it has several enhancements like completion and hierarchical directory like context. Some non-Python internal commands exist, all starting with the sharp character. But the most important aspect of this environment is the ability to load and use C and C++ code by means of Intromit. Let's load our previous demo class within this Python interpreter. Once the module is loaded, we can introspect it. Note that some code documentation has been generated. Other important characteristic of this environment is the persistency of the data. The whole context is saved at exit and restored again the next time the interpreter is launched. As you can see, also C, C++ objects are restored to their previous state. Now we are going to extend the example program with inheritance. We also add a virtual method, another one to generalize to base class. Once everything is typed, we compile and test. There is a convenience internal function inside Python backend called reload. With it, there's no need to restart the interpreter. The context status will remain unchanged. Now we create two more objects. The first one is of type derived. The second one is a generalization of the first one, of type foo. To test the virtual method, we just execute it from the three objects. As expected, when calling the method from generalized base object, the raised virtual method is executed. We could follow testing the rest of features of C and C++ into the Python interpreter, but that's reserved for future demos. Don't forget to visit the project page in Google Code website. Any comments, suggestions, bug reports, or pages are also welcome. Thanks for watching.